Can Katharina and Thomas, can I
before we start? Yeah, but
yes,
you have to make an announcement.
Yes, great.
Yeah, we're ready whenever you are.
Okay. Shall I make the announcement?
Sure.
Okay. I just want to hello everybody. I just want to let you know that our semester has started here in Düsseldorf. And so from yesterday on, we have two seminars running on COT and music. It's the one seminar that is led by Carsten Heisterkamp, and the other seminar is led by me. And we have some students here today with us. I think they are here are Sarah, Natalia, Maya, Nicole, Mike, and Robert. And yes, I just want to let you know that to give you a short idea how the structure of this seminar is. It happens every Thursday. We start from 4:30 to 7 every week, and the seminar has two parts. The one part, which will be the next 3 weeks, is that we try to learn and try to understand what an autopoietic system is and what are the point of views of you people on this theme that you are here. So we will watch in our seminar once again all the lectures that have happened already. And then we are ready to develop ideas how we can transform or how we can translate the structure of autopoietic systems into a sound, into a Klanggestalt, at least. So within 3 weeks' time, it will be like that the seminar becomes a think tank where we will try to develop ideas. And so I just want to say that you are too invited to this seminar to take part. Also, it would be great. I'm sure that we will have some more questions, and it would be great if we could approach you, that you maybe have some time in between and that you visit us in our seminar. That would be great. It is a mixed group of BA and MA students. And yes, and we are very happy to be part of this whole project. And yes, so and now we are happy to experience the lecture of Vincenzo and Thomas.
Thomas and Vincenzo. Thank you so much.
Okay, so Katarina, are you there?
Yes.
Okay, so we are ready to start the talk. Is that fine for you? Okay, good. Well, this is very nice to have. Well, first of all, also are we recording? Yeah, live. It's a recording on YouTube. So good. It's very good to have you here. We were 2 months ago having our first talk about this, discussing with Francis, and well, I will mention later. And now 2 months after, we made a collaboration, and we have some starting baby step results. But this is really nice when people get together and kind of develop things out of pure motivation and passion. So this is it's a very nice moment for me, and I'm sure for Vince as
yes,
well
absolutely.
to be here with you. So thank you for coming. Because not everyone has been following these talks previously, and particularly the students, which I'm also very happy to have here. I will give a little bit of context and acknowledge been mostly engaged in this. So this emerges from the art science group that was created by Francis and Katarina, and it has been an initiative that has come like recursively, periodically, forever in CLEA, Center Leo Apostel in Brussels. So it's something that becomes materialized finally with the arrival of Katerina, which is really good. So on the other hand, Francis and I applied for this grant, the origins formal scenario based on chemical organization theory and cybernetics, and we are a team of researchers which are working on other aspects, not on what we are going to mention today. This is funded by the Templeton Foundation. So one day, Francis came out with the idea of what made the dynamics of reaction networks, which is the topic of chemical organization theory, reaction networks and how metabolic systems synchronize and things like that. And this was also an idea that I had in the past. I think everyone who works around autopoietic systems and self-production.
I'm sorry to interrupt. Thomas, I think your audio is cutting out. I don't know if everyone else hears that.
Yeah, please confirm. Is it cutting?
Yes, it's cutting.
Yeah, it's very difficult to follow. So I think it's either your microphone, that the Zoom is cutting out when you're too loud. So maybe your microphone is too close to your mouth. Or
it might be.
Or maybe your connection. So let's try with the mic a bit further.
I'm just putting the microphone far from me. Is it cutting out? Is it cutting out?
No, it sounds better.
Yeah, so it was the first option because I put the headphones with the microphone and it was in front of my
this is
motivated mouth. So yeah.
Yeah, sorry.
Okay, so anything you have to, if you want to interrupt for something like that, Katerina, please do it. No need to wait, please, because it's the most important to have a good streaming. Yeah. Okay, so back to the Clear Art Science art group. Thanks to Katerina and Francis, the grant that we got with Francis, he suggested the idea to play the systems chemical organization theory. I will explain everything, but just believe me when I say play things. I started this group of seminars, this cycle of seminars about thinking of goal directness, chemical organization theory, cybernetics, and music. So I'm kind of following the grant. And these are the persons who first shown interest on, and then we started creating a seminar organization. Marina is everywhere, but I put her face here. Also a foundation that I'm working in Chile got involved. I'm from Chile, by the way, and many other people started adding to the seminars, and this really a nice of discussion.
Still cutting.
Okay, cutting again. It might be the internet. It's very likely. So I will move the modem.
If you can put the microphone even further, and hopefully it will be
it's
fine.
Opposite to my mouth. What about now?
We'll see. Yeah, let's see.
Yeah. So you tell me anytime that's. So we will introduce. So gave his talk last week. Made a very simple description of him. Applied scientist and amateur composer, and I'm a PhD in interdisciplinary studies, and I also have some music. I play the guitar here and there, and I also have these research interests. So his talk was he developed something for playing music under dynamical systems. But first, I will talk about the motivation of this group. So the Center is interdisciplinary. It's this interdisciplinary center, and the art science is the mix between like rational or conventional protocol-ish procedures and art, which freedom, emotional, explorative, not willing to create theoretical knowledge as science do. There's a tradition in the Centre Leo Apostel of conferences and gatherings between artists and scientists. And this conference in 1995 was a landmark on that. Einstein meets Magritte. So they made a huge conference with engaging artists from different disciplines, philosophers, physicists, mathematicians, and everyone kind of getting together to discuss about, from a disciplinary perspective, different society, the future of the world, and so on. So we all kind of in this group have an interest on, in a broader sense, about the world, and daring to explore venues that tend to be, or that are thought to be independent and talking in different languages, so they cannot speak to each other. We think that we can create the body language or the translation to connect these worlds. So the idea of this is exploring and experimenting around creation. And I put this meme here that looks like a chemical reaction chain. So that's why I felt interested on it. So getting more serious about it, there is something called generative music. So since musical forms are patterns of information, you can learn how to play the piano or the instrument following patterns of information. So play C, D, C, D. If the circle is this, you can. So one can music in any way we want. We can create forms of annotation, and form of annotation is in the end information. So we can map music to patterns of information. And computers implement algorithms to process information, and they do it much faster than humans. So if we have this capacity to create procedures, then we have seen that the development of computers have created some platforms, very complex, and some of them are related to music, as for example, Spotify. So then the question is, if algorithms have been able to create all these things, can they generate music? And this has been a long history of investigations. So this is the first one in the left. It's very old, kind of a platform to write music, and of course, write automatically if it's already in the computer. This other maps the voices of different instruments in a MP3, for example, so you can kind of watch the composition. And this other platform, the third one, is a platform for making other sort of music composition out of complex systems or networks of things that connect with each other. So there are lots of things in this respect. This one, the last one, is pretty much the same than the one before. So we are not the first in thinking about this. Many people, actually, Yanis Xenakis, someone who, and in our group, there is someone who studied that school, they developed this idea of playing the of thermodynamics or statistical mechanics in the 50s. So this is not something like we are the first in the history to think about playing a dynamical system, having a certain whatever structure. So generative music is a big field. But what we are more interested in is in the language of chemistry as a generative paradigm of nature. So this is kind of like the novel part of it, because we know that between the formation of Earth and today, today, what I mean today is like our current cognitive capacities, that we send spaceships to the moon. So our history of the world, of the Earth, is most related to the fact that that there are chemical reactions that tend to create the structures, and those structures evolve. Then you get into biogeochemistry, and then you get into biology, and then biology is as well, like when you look at the inner side of biology, you have biochemistry. So in the end, there is a paradigm of how nature has been developed out of chemistry. Of course, it can go up to atomic physics and quantum physics, and one can go even. But at least the periodic table and all the rules of chemical kind of have framed the development of all what we know. So it's if we think about it, these rules of chemistry kind of are responsible of everything we see. So this is a very simple example of biogeochemical processes between rocks and water and salt. So the structure which affinity to join to other atoms, and that creates reactions that end up generating spatial structures. So molecules can break apart or join, and we have some fundamental types of chemical reactions: combination or synthesis, where two things get together; decomposition, where two things separate; we have replacement in DNA and the kind of more biological processes where stuff gets replaced, and double replacement, for example, or combustion, or more. So there are certain fundamental structures that we have. Those fundamental structures, then repeated by different molecules, different types of species, generate the vast capacity of the world to be what it is. So chemical processes involve complex molecules and give rise to the substrate of life. And we have to jump between chemistry to how these fundamental single rules of transition between certain types of species end up creating the complex systems we see in organisms. So we have these complex molecules, and at some point, the complexity of the biochemical, the chemical reactions becomes such that life emerged. So the question here, how life emerged out of a geochemical soup? Because before life, there was no life. That's kind of obvious. So how did that emerge in the first place? How did this structure came out to happen? And there are things for this. There are concepts that help to understand this: self-assembly, self-maintenance, self-production, self-reproduction, self-production. So then there are models that say, okay, in this chemical soup, there were some processes happening. So molecules, groups of species, tend to self-assembly in space and self-maintain and self-reproduce. And that brings out the idea of having metabolisms, which are reactions that tend to self-create energy and all the resources that are needed for the system to re-execute the process. So this re-execution of the pathway is the footprint of life. The structures become more and more complex. This is a network database made in Japan about all the possible metabolic reaction networks known up to date. So this is a very, very complex. For example, human occupies one portion of this, then whatever insects occupy another, bacteria occupy this other, and so on. It depends on what organism you look, and you will color or activate one part of this network. So we can see all life as parts of this huge map of reactions, biochemical reactions. Of course, that's just the dynamical substrate. There is much more to talk about in this respect, like cognition and action and many other elements that are not mentioned, but at least for the operations of the metabolisms, this is enough. So we will remain here. So self-organization is somehow the norm of nature. Things happen in a way that they tend to self-organize in alive or in not alive systems, but self-organized in the end. So, but more interesting also is the fact that this self-organization tends to increase the complexity. And that's why we end up seeing complex life forms. If in the beginning we only have a geochemical soup, then we have basic organisms, and then we have evolution. So this is something really, really kind of not entirely understood by mankind, let's say. So there is a word called autopoietic, which most of you probably know, which means self-produced, basically. So self-organized and autopoietic patterns. When we see these patterns in nature, we tend to attribute them beauty. So this is typical self-organized flock of birds. All birds can move according to certain simple rules, and their behavior ends up being self-organized, very coherent and beautiful. So this is a drawing, a fractal or pseudo-fractal structure that it's found in microscopic views, probably a little bit. I just took it from Google. And this is the Oroboro snake that is traditional in I don't remember which culture. So if anybody remembers, please tell. But I know it's in different cultures, this figure of the snake or someone eating itself, and then always forever alive in yourself. So these ideas of self-replication, self-creation are around and attributed or connected to our perception of what is beautiful. And this has motivated artists to experiment. I will not dig much into this part, but this is made by inspired in autopoietic systems and done by one of the people in our group. So, and what about music? So this is the place where we say, okay, I give this explanation of how life emerges. This has some sort of beauty in it. So how can we map that to music? So do we have this self-organized autopoietic system? How can we put it in a score so we can hear the self-organization of a system? So that's the basic question. And now I will turn into more technical aspects and explain a little bit the chemical organization theory. So can people hear me? Hello?
Yes.
Yes, we can hear you.
Yeah, I got the impression that for some, imagine that I was just speaking to myself. But you are there. Yeah,
but maybe what you could try, Thomas, is to set up the microphone to don't autocorrect the volume, to get it fixed. So that might help into sending the voice like in a stream.
Still like cutting from time to time?
Yes, just we still hear you cutting and then.
So automatically adjust, correct that.
Yeah, disable the automatic adjust. You don't want self-correction in this case.
What about now?
Now it seems continuous, but the volume is low now. So maybe you want to increase the volume now.
What about now?
That's much better.
What about now? Yeah, probably now from all the introduction. Well, I hope you could get that. Yeah, I wasn't able to find the option before, but now I just got lucky and found it. So yeah, can you still hear me?
Yes.
Yeah, better.
Yeah. Okay. If there is any trouble, just let me know. So now it's important. This is the important part where if you don't get this, then it's going to be very hard to follow. The other part was motivation. So just to make a wrapped up, we were making the connection between chemistry as a generative paradigm of nature, then self-production and self-organization and self-assembly and all these selfish self-properties, how they relate to life. So then we were trying to hear the process of self-organizing, the process of life. This is kind of ambitious, but we can do it. So we just have to take the right method. There is a theory called chemical organization theory that studies reaction networks. I will give a very simple example. Just, I won't introduce the theory and the techniques and so on, but just make a very simple example so you get kind of an idea of what it is. So we will consider a reaction network, which is like what I was showing before, the metabolic stuff, but this is kind of artificial. So we don't have real molecules. We just call them S1, S2, S3. They can be anything, water, iron, or whatever, helium, whatever we want. But the reaction, or they can be also nuclear reactions. It can be protons, electrons, whatever we want. And we have the reactions that follow here. So the first reaction says when S1 gets together with S2, then S1 becomes S2 somehow. It's transformed. So the output is 2S2. And then S2 as well can turn into S1. S1 and S3 have a similar process than what S2, and S3 can become S1. And when S2 and S3 get together, then 2S1 become produced. So this simple network, we can draw it here. I made it with my own hands, very ugly, but you can see S1 and S2 get together and they become 2 of type S2. S1 and S3 get together and they become 2 of type S3. S3 becomes S1, S2 becomes S1, and S2 and S3 get together and generate 2S1. So you can draw the network. You can see the arrows and follow the arrows to understand that this generates a reaction network, as it was shown in the other big networks, the other examples. So it is very interesting to check that when S1 and S2 are present, so imagine that there is no S3 for some reason in the system. S3 is kind of sold out or whatever. It just escaped the system, or at that given temperature, the S3 leaks out from the system and there is no S3. So the only reactions that will happen are S1, R1, or R2. So there will be a transformation between S1 and S2 and nothing else will happen. So we can mark the subnetwork S2, S1 as the only possible happening of the network when these two species are going on, are present. Similarly, we have S1 and S3. When only S1 and S3 are alive, you will have only that happening. However, if you put together S2 and S3, because S2 and S3 generate S1, then the entire network will operate. So what we find is that the full network can be understood as the connection of independent dynamical modules. These independent dynamical modules can actually have overlaps, as in this case. The red and the blue overlap in S1. They don't overlap in reactions, but they overlap in species. The overlaps can be on reactions, can be on species. They can have different kinds of overlaps. So this creates a sort of hierarchy of sub-independent dynamical modules. And as I showed you before, in the big network, the Japanese network, which was in this part, I show you that some parts of the big reaction network correspond to different organisms. So this is it in this sense. Like life is a huge collection of reactions and organisms, some of those reactions, and they make out their living system out of that. This is just a very simple description of that. It's a reduced description. but that's it's a sort of this representative or conceptual example of the full phenomenon of life, is if we want to call say it like that. So the trick of chemical organization theory is that it helps you to mathematically identify all these independent dynamical modules, regardless of the size of the network and regardless of how complex it is. In this case, we can do it because we are smart and we can see what happens. But if you have 2 billion, you won't be able to find independent modules on your own. You will need the aid of a computer, and for that, make an algorithm. And the chemical organization theory provides those algorithms. So, as I said, interestingly, reaction networks self-organized into closed and self-maintaining independent modules. These closed and self-maintaining are just properties that define what the module, the self-productive module of the network it is. By closed, we say nothing new is created within the considered part. So, for example, going back here, if I have S1 and S2, and I look at the full set of reactions, I know that I'm not going to activate R3, R4, or R5 because I need S3 for that. So if I only have S1 and S2, I'm in a closed situation. Whereas if I'm in, if I am in the S2, S3 situation, I am not closed because I will generate S1, and S1 will generate all these reactions. So S1 and S2 and S1 and S3 are closed, but S2, S3 is not closed. So that's one way to condition what is the closed reaction network. Self-maintaining means all what it is consumed is somehow produced, actually produced at the same rate. So it's an specification, more mathematical, which I will not go in details, but self-maintaining means if I waste in whatever reaction, then I have to have another reaction that produces S1. So in this way, the operation of the network will be able to recreate its entirety. And that's the trick, to self-create all what you waste. So it's a sort of fully recycling system. So these are the articles. This is the article by Peter Dietrich and Pietro Speroni di Fenizio, who developed first this theory in mid-2000s. And the idea then is that you have a list of reactions, you generate the reaction network, and you find the hierarchy of organizations. What are the subsystems that can possibly work in a self-productive way? And this is another example. And the trick, the funny part, is that whatever dynamical specification you give to the system, so you say in the beginning there are these molecules and the reactions occur following these rules, when you set that up, then the system is going to evolve and evolve, but at some point, and this is for sure, it will fall into one of these systems. It might go to other systems. For example, here in this example, we have that AC is not an organization. So you might start your system having only A and C, but then the dynamics will make it evolve either to ABC or to BC, to A or B. So somewhere it's going to evolve in the future, but it's going to end up in one of these guys. It's not going to end up anywhere else. So, and that's wherever it ends, it has to be one of these. So these guys represent the stable, the self-organized possible patterns of the system. That's what the theory brings about. So now I will move to the simple chemical kinetic rule, because we need to devise something more kind of realistic, or not realistic, but at least having time evolution. So we can see the chemical reaction network moving forward in time. So we will imagine a chemical experiment, which is, this is a Petri dish just to show whatever, just to have in your mind a chemical experiment. We're going to make a chemical experiment. We know, what we know is that species move at all speeds and directions. So there is a sort of, chemically speaking, all molecules will be moving in different directions and speeds. If you add heat, for example, you know that molecular motion will increase. The speed will increase and the direction will be just anywhere. So they need to think, what is the chance or how come reactions happen having this situation? So let's say that I have the reaction AB goes to C. So I need to calculate somehow the chance that A and B get together and the chance that once they get together, they react. That's what defines the happening of a reaction. So for this reason, there is something called the law of mass action kinetics. Mass action kinetics. It says that it's the simplest possible way to make chemistry. It says that reactions will happen at a speed which is determined by, and now you need to read this, the chance that the reactants appear in the system. In this case, it's the product of the concentrations of A and B. So this is A and B, for example. So the chance that they get together, it's going to be proportional to the product of their concentrations. Because if there is more A, there is going to be more chance for the reaction. If there is more B, more chance for the reaction. If both of them are in higher concentration, even more chance. So it's directly proportional to how much of each of the type required there is in the system. It's going to be defined by a particular chance for the reaction to happen whenever they get together. That particular chance is called the kinetic constant. So then the formula that defines the happening of the reaction in the system, this happening is called flux. The flux of that reaction in the system, it's defined by the product of the natural speed of the reaction times the abundance of the reactants required for the reaction to happen. That is the most trivial possible way to define the happening, which actually assumes that the molecules are homogeneously distributed and bumping on each other without any preference. So everything bumps on each other in a random way with no preference. So then reactions, of course, will happen following this rule. So then you can count the chance or how many reactions will happen of this type per unit of time. That C is going to be produced at this rate over time. And A is going to be wasted at this rate over time. And B also is going to be not waste, but spent at this rate over time. Interestingly, we can note that the rate of the reaction does not depend on the products of the reaction. It only depends on the event of the reactants getting together. And just for notation, we will call V bracket I the flux of reaction I for I 1 to n. When we have more reactions, we will call the flux in this way. So the flux is like the concentration of the reaction. The concentration of the species is going to be denoted in this way. So now we have all the elements to describe the evolution of a chemical system. So now it's time to make an analogy with music. Since we know that that self-organization ends in a closed and self-maintaining network, which is what we call an organization, we explore the different paths towards organizations as sounds. And that will be hearing the process of self-organization. So in a certain way. So how do we do this analogy? The types of species or the type of reaction will be different instruments. The concentration or the flux will be the pitch. So the more flux, the higher pitch. The higher concentration, the higher the pitch. The structure of the network will be the rules of sound generation or sound change, let's say. Sound is going to change according to how reactions happen, and reactions happen according to the structure of the network. And the kinetic rules, which is what I was just explaining, the mass action kinetics in our case, and some modifications that I will show, will define or will determine the sound transitions. Also the initial state, it's important. The system begins in an initial state. So this analogy, what we have here, we say now, and we hope that this is the case, this is the beginning of the exploration. The beauty of life can be musically expressed by using COT as an interface language. So we think that this is our scientific claim. Okay, so now Vincenzo is going to explain the workflow. Vincenzo, are you there?
Yes, I am. Can I take the screen, control of the screen, maybe?
I guess. I think you can tell me move. It's everything.
Yeah, but
if you say just go ahead.
I think that the presentation is messed up here, so I think it's best that I think it's best that I go with mine, my
okay,
version.
you can share.
All right,
you will have to share your own screen. Is that okay?
Yes, perfect. Okay, if you want to share. So I'll just
in the meantime, this is a good time.
Can you see my screen?
Yeah.
Perfect. All right. So let me just see if I can start with this presentation. This part of the presentation. Let me just. It doesn't. Oh no! Oh my God. Sorry. Too much. So many thanks for this opportunity to join with Thomas in this fantastic journey. It's been great to have 1 week of experiments with him. Now I'm going to hook a little bit into the presentation that I gave last time to see how it links with this part of the story. Last time, 2 weeks ago, I introduced an approach which was basically based on dynamic systems. There was a couple of functions that I represent here as F, and these F functions were run, and I collected the orbits of these functions produced with some input. Then I gave this data, which was represented as a set of integers, to a function which produced a score in a format called Lillipond, and then this score was converted into a MIDI file, and then this MIDI file was converted into an audio file. So the thing that I didn't have the opportunity to explain last time was the mapping of the orbits into nodes. So we simply have a set of integers, and this can be produced by different Fs, different dynamic systems, and this is what happens with the experiments that we are going to describe today. So instead of using my functions, we hooked this into the chemical organization theory code produced by Thomas. But in the end, this code produces a number of, a series of numbers. And these numbers are first converted into integers, and then these integers are converted into nodes. According to the following simple algorithm, suppose you have a number like 42, you divide it by 12 because there are 12 notes in an octave, and you get a quotient and a remainder. And the quotient represents which octave you're playing, you're activating, and the remainder is the note within that octave. So for instance, 42 becomes third octave, sixth note, which is an F. So, the other aspect which I added is that if the notes are equal, so the current note is equal to the previous one, instead of playing it again, I let the previous note last longer. So this very simple setting, with this very simple setting, it's possible to convert these series of numbers into music. And so Thomas and I have been instrumenting my code in order to use, instead of the functions that I presented last time, we hooked the COT code that he created in a Jupyter notebook. Of course, we had to do a number of adaptations to this code. For instance, originally it only was based on 3 voices. Now we can have up to 5 voices. And it is important for me to clarify that what you're going to see in what follow is just raw experiments. So we have to do a lot of things more in order to get more interesting results. But I saw from Thomas that the potential is amazing, nearly infinite, and he has a lot of ideas, and so we are going to start working on this very soon to create even more interesting music. Yeah, a very important aspect which I learned by starting this work is that whatever you do, it's very important that it is reproducible, and so it's very important to store the experiments in a clever way. So I'm going to create a repository of experiments and the corresponding outputs, because in this way we are going to at any time go back to a certain past configuration and run it again and be able to reproduce the same results. Okay, that is it from my side. I will now stop sharing. Is that okay?
Yeah, I will go back to the talk.
Thank you.
And the workflow, so I can skip all that now. You will see the workflow. And no, I have to stop share and share again the full. First make the slideshow, otherwise, yeah, current slide. And now, well, hello. Can you hear me?
Yes.
Yes.
Yeah, yeah. It's that my I'm not so smart at this. Okay. So now you tell me if you see yeah. Okay, so current status. So we will start the experimentation now. Back to our simple reaction network example. We have that. We know from this simple example that there are 3 possible organizations, 3 possible ending states. S1, S2, S1, S3, and S2, S1, S2, S3, right? Do you remember the 3 modules? So what we will do here, what we will do now is to hear the different ways in which an initial conditions for the system end up on each of these states. So the system we have is 3 species, S1, S2, S3, and 5 reactions. So we will play the reactions, that is the fluxes, as if they will be the instruments. So the fluxes will be the instruments, and we will define first the three convergent states. So the example, remember, is it begins with S2, S3, which is not stable because it will generate S1, and then S1 will kind of adapt with S2 and with S3, and something will happen. But we know that from the beginning state, S2, S3, mass action kinetics will lead the system to become S1, S2, S3. And then depending on the conditions, you will get the three types of stabilities. Actually, when K1 is larger than K3, the constant, the natural constant of reaction 1 is larger than the natural constant of reaction R3. For these conditions, we have that the system stabilizes in the concentrations. You can look at this concentration diagram. You start with only look at the green is S3, the orange is S2, and the blue is S1. So the blue begins in 0 because we start with S1 equals to 0. We only have S2 and S3, and both you can see there they are in number 5. They have the same value and they tend to be very similar, very equal. But then at some point, S2 dominates and S3 loses the fight, let's say. And S1 stabilizes in a very small value. You can see that? You can do the same with the fluxes. You have that all the reactions here, the happening of all the reactions following the mass action kinetics will evolve in a certain way. And because S3 goes away, all the reactions linked to S3 will fade away as well. And only the reactions that correspond to the happening of S1 and S2 together will survive. You see? Similarly, you can see the same changing the concentrations and have a very, very kind of, because this system is symmetric, right? S1, if I switch S3 by S2 in this system, I will get the same system. So actually, the evolution of S1, S2 or S1, S3 is exactly the same. It only will change some of the colors, but nothing else. Look, it's blue by green here, blue by green, and here it's orange by green. Is that? Yes, orange by green. So you can see. And the other case, it's when K1 is equals to K3. So the system goes from S2, S3 to S1, S2, S3, and it stabilizes in S1, S2, S3. Here we cannot see the orange curve because it's right on top of or behind the green curve. Because of the symmetry of the system. Again, it's a very simple example. That's the reason, because it's very simple. You will see the symmetries. So now I will play the pieces. So these are short, so it should not bother you for too long. So I will play the S1, S2 case, so the above case now. Did you hear?
Yes.
Yes.
So the S1, S3, it's going to be very similar, but not entirely the same. It had a little bit more freedom. This because it's discrete dynamics, nothing will be exactly the same. Remember, we are playing the fluxes, not the concentrations. So that's why we can hear more than 3 instruments. And the S1, S3 stable, the S1, S2, S3 stable, this is the most boring possible case. That's it. So it's fully stable. So now, okay, one can feel very disappointed about, okay, all this huge round to end up playing like very boring notes. Well, yes, but this is the first very simplest example to show that self-organization of chemical systems following the simplest mass action kinetics can be listened. And then one learns this synesthetic feature capacity to hear and see the plot and identify what it is what. So that's something that I think it's very nice for researchers, for scientists to learn to hear the curves. But of course, we were not completely satisfied with this, and this is too simple. So we gave some more time to explore a little bit more non-trivial changes. So first way to be non-trivial is to not start with the same concentration for the species that are symmetric in the system. Remember that S2 and S3 can be exchanged and the system doesn't change at all. So if they have the same concentration, it's like they are the same molecule, right? That's why they were plotted in the same one curve over the other in the results. So now we will give them a little bit more of freedom. They are different. And we may, and we worked out a parametric. It's not, now things are not so simple numerically. And because of time, of course, we only seek for a parametric choice that helps to obtain S1, S2, S3 for a long time. We couldn't manage to find, maybe it doesn't even exist, or maybe the parameters are extremely small, the range of parameters. So starting with dissimilar concentrations, you still can end up in something stable for S1, S2, S3. So the system, the best I could get, remains for S1, S2, S3 for quite a while, but ends up collapsing in S1, S3. And it looks like this. So you see, the beginning of the system, everything remained stable, but then at some point, the green says, like the blue says, I give up, and it goes away. And then green dominates the system. You see, and that at the level of reactions can be seen in this other way. So then I will play this other one, which is slightly more interesting, which is S1, S3 unstable. So here it goes. You hear? So that's the process, the listening to the process of these instruments, these species fighting or striving to survive. And then in the end, boom, the one that survived tell the last note. So as Vincenzo was saying before, this is the way to go forward and to try to discover dynamical procedures or dynamical regimes that will lead to more interesting musical features. This is still too simple. This is still like because it's pure simple oscillation. There is not much much longer or much, let's say, more complexity than everything oscillating at the same rate, which is very simple. So in our last half an hour, maybe half an hour ago, we were trying to find, no, there is still some other system that it's slightly less trivial, which is non-symmetric start, different rates. And we introduced now a periodic inflow. What does that mean? That every certain time, molecules of type S2 and S3 come into the system. They enter in the system. Every certain time they come in. So because of these inputs, we get inputs here. You can see the input, boom, there is a jump here. There is another jump. It's because there are inputs. of species. So this creates something more interesting that are rhythmic patterns, not so tiru, but something happening, and the fact that we are introducing, we open the system, and now it interacts with an environment which brings in species of certain types, and that creates a much more rich sound atmosphere. Still, I wouldn't call it musical, but there is a much richer sound atmosphere. So yeah. So yeah, I mistakenly played the one that it was the slightly more complicated than this one, that I have no explanation. So I skipped the other, which is intermediately complex. But this one is the one that I just played. It's exactly this system, but it has an extra complexity, which is introducing not just inflow, but also outflow. So the system is open in both sides. It can receive stuff from the outside at a periodic pace. So every 10 steps, let's say, or 20 steps, you receive inflow of one kind. You receive inflow from other kind at a different pace. So there are two periodicities involved in this last system. So that I'm sorry, but also for the sake of time, it doesn't really matter if I show the other intermediate case. So this last sound was a very similar system to this, but just with an extra little modification, which is bringing biperiodicities. So S1 comes in every 10 seconds and S3 comes in every 15 seconds. So the fact that they come in, the inflow comes in different times, it generates this more complex rhythmic pattern. So this is it for now. I will make the small conclusions so we can discuss.
Thomas, I sent you by email another rendering of this final piece. Yes. Could you perhaps let it?
I think I have it here. It's the FLAC file, isn't it?
Yes, it's a FLAC file which I sent you by email.
Yeah, this is an orchestrated version done by Vincenzo.
Isn't it? Yes, 10 minutes before the beginning of the presentation.
That's the way. Okay, let's play that last piece, which I don't know if it's like whatever, but I found very interesting the last piece. I think it has parts. Yeah. So it's not music yet, but it's at least there is some complexity to find intentions and changes. Okay, let's go. Nice. I don't know how to stop this FLAC file. Stop sharing just to control the computer properly. because probably it's gonna play forever.
Yeah. It's a very indisciplined music.
I don't know how to stop it. Well, I at least can mute myself.
No, we are not hearing the music now, Thomas, so it's fine. When you stop sharing, then the music stopped.
But we could still hear you, so everything's fine.
No, not anymore, probably because he muted himself. Oh no, now it's back.
Yeah, I mute back and unmute, but it stopped. It just played twice. I don't know why. So yeah, I will share screen again just to get to the conclusions, because now after this exploration, we sort of have kind of a much better understanding of this. So do you see the discussion?
Yes.
Slide?
Yes.
Yeah. Okay. So my computer is reacting very slow to what I said, what I tried to do. Okay, now, no, still, well, anyways, I will just continue speaking. I wanted to see your faces, but I cannot open them. So the discussion, the power of inflow and outflow. That's the thing we discussed with Vincenzo. Inflow and outflow in nature, if we think there is a rhythm, nature has its own rhythm. We have the motion of the earth that has a certain periodic rotation. So we receive light in a certain amount over the day, and then at night there is no light. But at the same time, we have the attraction with the moon that is also, it has a simple periodic, but also a wider periodicity because we also rotate around the sun. So there are different periodic motions or different periodic features in the way we live in the world. And all these periods, which are many and very different between themselves, they can be understood as inflow of a certain part of the world. Whatever rock, for example, it receives wind with a certain periodicity, it receives sun with a certain periodicity, or bacteria or birds that come in and come out. So that everything has its own, every single process independently from each other, they all have their own periodicities, their own rhythms. And all those rhythms together come together in every place actually, and induce the happening of other rhythmic behaviors. So this is what we were kind of very much surprised at understanding, that the self-organization process of the stuff that we are seeing, it's going to be always strongly dependent on the openness it has to the outside, and in both ways, receiving and giving. And then the internal autopoietic machine inside is going to self-organize to adapt to this external environment. So, and that process of adaptation, it has to, of course, respect the cycles of what is coming in, and whatever, if there are cycles of processes for living out, taking things out, the self-organization process will respect that and will be somehow mirroring the external dynamics, but it's not going to have just the external dynamics. It's going to create its own structure inside. So there is a lot of power for inflow to control the music we will do, and or the sounds we will plot, let's say. So this is something really interesting to say, that we understood that the structure of the network and the connection to its environment, it's significantly related to the type of music or the type of sounds you will find. And the fact that behaviors are not entirely aligned in nature, so nature is not do-ri-do-ri-do-ri-do-ri. Nature is much more rich. And why is it rich? It's because not all things have the same periodicity. Different periodicities locked the system for some periods in certain behaviors, and then they unlocked and locked in another period. So the fact that we have these not entirely aligned behaviors creates a strange, I call them strange just to make it very simple word, strange cycles. So the rhythm of nature is strange, like as we are plotting now. So that this is kind of like more maybe intuition wise side of the conclusions. But the other part is that the mapping we are doing, it's too simple, because the map, it's going to attribute higher pitch to higher concentration, because the dynamics is by construction very close to continuous. You will always have chromatic lines. It's very hard to have a non-chromatic interval, so a third or a fourth interval. It's very hard to get because you will need a very strong jump from one concentration to a much higher value in 1 second, in one time step. And that doesn't happen for the kind of dynamics we are seeing, we are plotting. So instead, we can change the mapping and not map just the pure concentration of one species as if it would be an instrument, but we can make organizations to be the instrument. Not species, but organizations or collections of species. So if organizations are the instruments and not just the species, we'll have another way to represent the note to be played by the instrument. And that, of course, requires to scale up to much bigger networks, not with 3 species, but with 20 or 70 or thousands, as it is in normal nature. So then we will be hearing, understand, or building up the right mapping. We will be hearing the real thing we want to hear. So this is just very simple, kind of functional toy lab to make sounds out of reactions. But now we need to scale up to larger reaction networks. So subnetworks play instruments, and also understand better the mapping of or the connection of inflow and outflow, and also introduce, why not, some other physical or spatial processes, which we are not introducing here. We are not bonding molecules in space. We just bond them in an abstract way. They get together, but there is no spatial bond. So we could also introduce space, and that will be like molecular dynamics, like full molecular dynamics way to play them musically with instruments. So if Vincenzo, do you have anything else to say? I think this is it for me, at least.
I just would like to mention that there is a big assumption here, which is the use of notes. But in principle, we can change this and map frequencies, which means that we would not have a translation into a scale. I mean, a predefined tempered scale of notes, but we could listen to sounds. I mean, and then we would not have the chromaticity. We would have something maybe strange to hear, but certainly worth investigating also. Yeah, okay. And another thing that I would like to hint, to suggest, is that maybe we could play together fluxes and, not one after the other, but together, the different components, and see if they have a musical value together.
Mm-hmm.
And it would be very simple to do this, because it's just a mixing.
Simple for you.
Oh, it's really easy. I will show you.
Yeah, I'm kidding. Well, okay, so this is it. Thank you for your patience, and now we are open for questions. If you want to see the code, we can show the code, or any.
Yeah, I have a question actually. So at the beginning, you show some graphical representations of self-organizing things in general. Would it be interesting maybe to take existing pieces of music and using the same algorithm that you took, take a representation in terms of fluxes and all the other reactions that you have, and then see how a certain piece of music is represented in the species and those kind of things. And then it will be like a way of cheating if you get an assignment like a make how's it called, a variation of a certain piece of music. You just introduce a species here and there, and then you get variations from the original piece. So that would be like having different variations of a certain piece that already exists. It also will help you to have a kind of a different representation of how to compare a piano sonata from Beethoven and a fugue from Bach, for instance. So that will give you something different. So would that be interesting to investigate? That's my question.
Yes, I think so. So if I understand correctly, you mean that you take as input an actual piece of music, and you see the concentrations of the notes, you interpret them as a density of molecules, etc., and then you use it as a starting point, for instance, or I don't know, as a set of input for a neural network, for instance, to learn.
Yeah, exactly. Then you see a representation of the music in that sense. And then you can apply modifications back on the neural network, for instance, and then see how that changed the piece of music.
I think this is a great idea. Thank you very much.
You're welcome, Enzo.
Yeah, it's really good. It's like the inverse problem. So what will be the reaction network of that piece? And I'm sure, well, not sure, but I sort of kind of guess into what is the verb of intuition? I intuit. In Spanish, we have a verb for that.
You can say maybe I sense or something like that.
I sense, yeah. I sense. I sense that mass action kinetics will not be the right partner for the dynamics, because mass action kinetics is it's too simple. It doesn't allow for this feeling of having a pause, like stop, no sound. You need to lower everything to have a pause, to go down. If you have action, you will have more action. That's mass action kinetics. If things are there, then they will remain there. So I think it can some certain I don't have the intuition for what can be the exact dynamics of a whatever piece, but I smell that we might need some spatial structure associated to the chemistry. So it's kind of like a path, something like diffuses and goes here and there and explores this and then goes back. It didn't work. So something like guided. There must be, and I've seen in the artificial life people kind of in the community, they incorporate this idea and they call it the beacon, like Spanish farol. Beacon, like this thing that guides, it tells you this way, that way, that way, and you introduce one particle only that guides the rest. So like the boss kind of particle. And probably this will be a way to simplify the deconstruction or the reconstruction of the piece by having certain kind of person or molecule or type of molecule that guides the other or chooses what types of dynamics has to happen at each point, so the system, the piece can be reconstructed. I think that could be a way, because the mass action on its own, might be too complex, too many dimensions. But yeah, it's doable. It's doable. So thank you, Boris. Nice.
You're welcome.
I had one question. This is Andy.
Yeah,
one
hello, Andy.
question and one comment. Very, very fascinating, by the way. Firstly, self-assembling patterns in nature are beautiful. Man-made musical patterns have coherent human meaning, but can be very simple, repetitive, and therefore limited in beauty. And of course, people can also be limited in their emotional capacity to appreciate. So my question is, where's all this going, in the sense that if you can imagine, like my own work focuses on collective intelligence and creating self-assembling decision-making systems that might be, have an IQ of 1 billion, be able to self-assemble to have vastly greater capacity to answer questions. So turning that to music, is it possible to self-assemble? This is, you don't have to answer this question. I just want to throw it out there. Is it possible to self-assemble musical components in a way that's far more beautiful and therefore far more emotionally powerful, perhaps producing extreme states of euphoria in a greater percentage of the population in a more reliable way? That's my question. And I have a comment, but maybe you can say a word on the question first. Like,
well, I think that following the Boris theory, that might be possible. We will have to start from those that we already know that produce that kind of feeling, recreate the network, and then explore around if we can sort of create a greedy algorithm that takes the direction of highest emotional impact always. I change the network this way and then that way. And luckily, one can arrive to something that strongly improves all what it is known so far. Also for beauty, for any feeling, but it's a little, well, we are here to think, not necessarily to do. But so think wise, it's possible. Yeah, for doing it, it might be a very ambitious enterprise, but possibly yes.
So the comment is the key element missing, that appears to be missing in this approach, is the ability to map these self-organizing musical patterns to emotional response. And I say this because my specialization is human-centric functional modeling. And I believe that functional modeling approach could be of value here because it creates the potential to model the transition from one musical pattern to another in terms of maximizing the creation of entropy within the emotional system. So when one is considering how to vastly increase emotional impact over what's possible for any music today, one has to chain together all those emotional responses. One last comment, and that is, it would be interesting to see how one could methodically map out all of these musical patterns in order to gain the ability to navigate that emotional state space to wherever you want it to go, wherever you want to go to. That's it.
Do you have a comment, Vincenzo?
It's quite interesting. I mean, while listening, I was considering from one side, if you see the problem of going for a maximization of the surprise, the entropy, let's say, you can probably create a track, a piece of music that is not very much appealing. I mean, I don't know how aesthetics is related
by definition, it could not maximize impact emotionally if it's not appealing.
Yeah, I understand. But emotions can be of different types. When Stravinsky first produced his Sacre, that is now considered one of the greatest masterworks of contemporary music. I mean, the reaction of the audience was that they wanted to kill him. I mean, because it was completely unexpected. It was reproducing the prehistoric festival of the arrival of the spring, and it did this with such a variety, with such a richness of new elements, that it is now considered as something as a milestone. But at the moment it was presented, it was not very much accepted. So I was wondering now, between these two aspects, I mean, emotion can be positive emotion, but even negative emotion, let's say. So I was wondering, maximizing
that's actually a really important part of human-centric functional modeling, which is understanding the context. If you want to so part of modeling a function in some functional state space, like the emotional space, for example, and gaining the ability to reliably navigate, is understanding the context in which that function is. For example, if the context is, I don't know what time this music was made, but the context is
1917, I think.
Not a 1917 audience in a particular country, in a particular part of that country. The idea is that in order to reliably navigate the emotional state space to, from whatever context you're into, whatever end emotional state and context you want to be in, you have to be able to reliably navigate from any such context. So perhaps if that piece had started with something that didn't assume a particular point of view, but on the other hand, was more general and was able to navigate that audience towards a well-defined emotional state and context where they could be navigated to somewhere else more reliably, maybe that's the way to do it. So maybe this composer you mentioned was brilliant, but maybe he lacked the capacity to navigate a particular audience in a particular context, in a particular emotional state. Maybe he made those assumptions. Maybe he didn't have the capacity to write music that didn't need to make any assumptions whatsoever, because it started at a common ground and was able to use that common ground to navigate everyone reliably towards a common place where it could radically increase emotional impact.
I see.
Yeah.
Thank you.
Emotional impact, as you say, it's context dependent. So then I guess it's more practical maybe to simply think, okay, we will assume this is our context, and try to work for a particular context, not because as you say, like the idea of talking about beauty and all these things, it's not so simple. It's very complicated to make everyone happy with beauty, you know.
There seem to be patterns
for
though.
Everyone. Yeah.
There seems to be.
Yeah.
When I say that they're, what I mean is when you look at things that go completely, when you look at speeches, for example, that capture an entire audience and make that entire audience stand on their feet. It might be millions and millions of people. There is something in those people who are particularly talented at that, where they're able to find common ground.
Yeah.
And start from that common ground towards ideas that maybe if they started with the end ideas, they would have lost some people. But they start with something that everyone gets on board with, something that's universally human. So that's the point. Yes, we all see beauty a different way, but we also can see beauty the same way. The challenge is navigating a large audience, or navigating the majority of people most reliably towards a certain
I understand. I understand. I think the point is clear. It's trying to, but for this, I think it's something doable. It's a huge extension of what we do, to incorporate emotions to the. We are just playing sounds for the moment, and then Boris is suggesting to recreate the network of a known piece. And then, as I said before, we could at the start, because known pieces, we could kind of, between quotes, say that we know their emotional state navigation. Let's say we can say we can do it. It's quite. I have my doubts. I guess many people might have their doubts that we can do that, even for pieces that everyone recognizes that they are good.
And
because
just recognize that I'm solving the exact same problem.
If you listen to some piece, you might have a particular feeling for it. You find it beautiful for reason A, and the other person find it beautiful for reason B. So that, but this is not to drop down what you say. It's just to say that this is very complex problem, and this can, I think it's something that can be advanced, but I don't see exactly how to do it at the moment. But I suggest that maybe neuroscientific research, activation of emotions at the neural level, because there are devices now that, oh, this is happy, this is sad. Maybe this could be a way, and in this sense, the chemical reactions are devices that create self-organized processes. So we could start by mapping the emotions that are activated by different types of self-organized processes, and that will be a way to start. But I don't see this as a step towards a universal solution of creating all emotions from music. This is something I don't see directly the connection. But it's interesting.
Hold on. Just to be clear, I believe this is 100% doable, and I also believe that I've come up with this. So firstly, you can describe, in my view, any system in the human body in terms of a functional state space, so a space of functional states, and this space is just a network of nodes connected by relationships. So one functional state space requires pretty much the same functions to navigate as another functional state space, because it's just an abstract space. So the bottom line is solving this problem in conceptual space, which I believe I've done. You've also then solved the problem in emotional state space and other state. So and by the problem, I mean the problem of self-assembling patterns in order to vastly increase capacity to achieve some overall impact. That's it.
Yeah.
I believe.
Yeah.
Sorry.
Go ahead.
We had a question from Serena. She raised a hand, but you went into.
Oh, yeah.
I'm wondering
sorry,
if you would still
moderator.
like to ask a question.
It was less of a question, more of a comment to what you were saying. I love Andy's idea and thought, because I was thinking about the same thing. And of course, it's very difficult to sort of compose a piece of music that everybody's gonna like, and it has a lot to do with associations and familiarity. And those are just like, this is not to say anyone's wrong. Those are just a couple thoughts that I had that should be taken into account, and I think those can sort of be functionalized in a way. There are a couple of videos on YouTube. I can send a couple of links if I find them. Just as an additional thought.
Thank you.
Yeah.
Vincenzo, Thomas, can I share some
Please.
thoughts? Well, first of all, thank you very much for your approach. I think it is super intriguing, and to me, it's a point of entry, how to deal with it and where it can be taken. This is where we can take it. It's really, so really thank you for this approach. Just three ideas. The one is, I think it's really great that you started with such a simple model, that you just have these 5 reactions and 3 subsystems. And I wonder if we in Düsseldorf for our seminar, if we take it so that we have the same, that we take it from the same basic model. I think this just to make it comparable. The developments. This is what I'm thinking, and therefore we have to study this for you simple model, but for us it's not so simple. We have to first of all to understand it in the seminar. So my question would be, Thomas, if you would be up maybe to come into our seminar and explain it one more time for us, if this would be okay. This would be fantastic.
Yeah, of course. Vincenzo, are you up?
Oh yeah, but my contribution is very limited. I mean, I just provide the back end to produce the music. You're the master.
But we can do more exploration. I mean, more hands and more ears will produce more interesting dynamics. So I think we are now, I mean, everyone can explore with this tool now. It's very easy. We can give a tutorial maybe next time or in the future. After a few more talks that are scheduled, we could do a tutorial. And by then, probably we will have something better, because this is kind of rudimentary software for the moment.
Yeah.
But yes, Christian, of course, yeah.
That's great. That's great.
Of course.
And the other 2 things is the direction where it can be taken. I think the direction you have taken now is that you take a reaction network and you use it to generate complex music. And this is the questions your ideas are revolving around, how to make it more complex. This is one approach. The other approach, another possible approach is trying to make the network audible, which means to make it even more easier than you did it, to even more downshifted, so that the structure of the reaction network or of the system you started with becomes clear to the ear. This is what I'm thinking about. Do you understand what I mean? Do you know what I mean? To make it more. So this is just what I'm asking myself. How would it sound? How far can it be? How far could be the sonic representation? How far could it be downshifted that one can follow the reaction network in its most basic form as you presented it? I don't know. These are just ideas that are.
There is one way that we could do very quickly with Vincenzo. Well, Vincenzo could do it very quickly. I say we, but it's him really. So what because at the end, may I share screen?
Of course.
So I think we will somehow kill the 2 birds with one stone by doing this, which I'm going to propose here. So I was just discussing with Vincenzo. Let's say we have the 3. My keyboard is broken. I cannot write in this window. Maybe I could try the chat. For some reason, it's not. No, my keyboard is not responding. Well, but anyways, we can all. But I can draw with the mouse. Great. This is very ugly, but still possible. Yeah. So, Okay, so imagine we have species 1, species 2, and species 3, right?
Yeah.
And we are now, this is analogous to instrument.
Yeah.
Instrument. So we have 3 instruments. So if concentration, let's say, can go 1 or 0, just to make it very simple.
Yeah.
1 or 0, okay? So we have 0, 0, 0. And this will be for our previous thing, C1, 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 right? And let's say C1 and D1 as the possible nodes. So 1, 0, 0 would be D. I'm just making one with no sense, but okay. D1, sorry, D1, C1,
C1.
And C1. Because I only change one of the concentrations, then I change one of the sounds.
Yeah.
Okay. But what if instead I say that this is C and this is D, and then this is E, and this is F, and then this is G, 0, 1, but
Yeah.
0, 0, 1. This is G. So I make only one instrument, which is composed by the configuration of the 3 species.
Yes. Yes.
In this way, we kill 2 birds in one shot. The first bird we kill is that we will have something more simple. We will have only one melodic line, and we will be able to somehow hear in a simpler representation of the network.
Yeah.
Right?
Yes. Yes.
And the second bird we will kill, this is this, let's say, simpler, and the second is the non-chromatic. Why it is non-chromatic? Because a change of the concentration in S2 is not going to reflect necessarily in a change in a chromatic change of this instrument, but might switch, for example, from C to E, only changing the concentration of S2 here. We see a third interval, major third.
Yeah.
Da, 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 da. So we can do that with changing one. Instead, this one will be, for this instrument, you will hear da, something like very chromatic. Chromatic, you know, it means like a small jump, smallest possible jump. So I guess this way it will be an easy, it will follow what you were just saying.
Yeah. And this means that you just play with the concentration, right?
For now, or flux. It can be flux too.
Yeah.
It is analogous.
Is it this is what I didn't understand really. Is it where's the difference between flux and concentration, or do you put it at the moment you don't have a division? It's one thing.
No, there is a deep difference, and I like that you ask that, because this is the big difference between object ontology and process ontology. Isn't that so, Francis? Where it depends on where the flux, because the simple thing is, when we think of a living system, which is a reaction network, right? Yeah. We naturally tend to attribute ontological existence to the object, to the species. Yeah. So species are sort of little homunculus, little guys that want to connect and create other guys, and they make up this city. So they are kind of cars, you know, horses, or whatever sort of little agent that is alive. And the reaction is just the way they interact. But those guys interacting are the species. not the reactions. The reactions are just the interactions. You can flip the understanding to a process-based ontology, where species are just waste of resources, like dead resources, right? Like just stones around, and reactions are the active guys who are trying to exist, who are trying to happen by using these resources, and they strive for happening.
Yeah.
So then a living system or a sort of what is the word, metabolic pathway or something like that is the cooperation of reactions. So reactions will cooperate to reproduce their own existence, because when they happen, they exist, or they exist when they happen. Whereas molecules do not exist when they happen. They exist, they are given. They just try to avoid reacting in ways that are negative to them and try to react in ways that are positive to them so they can reproduce. So there is an ontological kind of biological, bio-ontological conditioning towards species in our normal understanding of chemistry.
Yeah.
Whereas I think that biology, in my opinion, emerges from the opposite ontology. Reactions are striving to happen, and molecules are dead resources, and then living systems are the metabolic pathways, not the species that are in the cell. You see?
Yeah. Yeah.
So that's the difference.
Yes.
And that's why I prefer to play fluxes and not species.
Okay.
But no, that's just a joke. It
no,
could
no,
be
but
anything, yeah.
Yeah, but
because they are kind of analogous, yeah.
Okay, but so
mathematically speaking, there is no. They both need each other for the system. So
yes.
Mathematically speaking, it's just two faces of the same coin.
Yes, but you were taking it from the flux side of things, right?
Because we have 5 reactions, we could play 5 instruments. So that was kind of richer for the first exploration. Yes, but we were playing concentrations too. We were playing concentrations. Yeah.
Okay. What was the concentration? So the flux was the pitch, right? Flux was the pitch. Is that right?
And when we play concentrations, concentration is the pitch. But we didn't show the concentration, the mappings of concentrations associated to pitch. We only played today the mapping of fluxes associated to pitch. Different reactions, different instruments. The other choice is different species are different instruments.
Yes.
And the concentration would be the pitch. And the choice that we were just discussing is like, now no single molecule or no single flux is an instrument, but a collection of them. And you create a mapping for different states of the system to be different sounds.
Yes.
Yeah. So that might be like
my original proposal, which maybe is a little bit too obvious, is that the species would be the nodes and the reactions would determine the change in the nodes. So the reactions would be the changes in time. For that, you would probably need a discrete version of the reactions, because otherwise you would have continuous nodes going up and down, and then the concentration would simply be the volume. So that was my original idea, which may be more transparent compared to what Chris was speaking about. So I think you need to experiment with all kinds of different translations.
Yeah, the one that Francis suggests maybe is the simplest of all of possible. Because those species that, sorry.
I just wanted to add that I think what Francis is proposing goes well with Boris's idea of taking an existing composition and then infecting it with this data in a way.
Also, yeah.
I would perhaps have a concrete proposal for this mapping that Vincenzo said that could be changed, to connect it more to the frequencies. I think if one would do it as follows, you fix one frequency somewhere in the middle of the A, for example, and then you map, instead of to nodes, not to nodes, but even not to frequencies that are used in usual music, but you map just to fractions of this one frequency. So you make the numbers correspond each time with a fraction of this one fixed frequency. And then I think you will capture harmonics in some very, very complex way, yeah? But at least you will capture the harmonics that was once detected by Pythagoras. Huh? If you remain in fractions, you fix one frequency and then you go to fractions of that one frequency. And you see that the numbers go to fractions that will more or less give the keyboard of a piano or something like that. So the fraction should not be much higher than where the piano goes and much lower than where the piano goes. Or organ or whatever.
We end up with notes in the end.
No, then you don't up with notes.
Notes before Bach.
Yeah, before Bach, not tempered.
Not tempered, yes,
not
but
tempered
notes nevertheless.
Yeah, but you will not end up with notes that can be linearly on a keyboard.
No, exactly. Only on a violin. I mean, on a type
yeah,
of
on a
instrument.
violin, yes. Essentially, but not on an organ, for example. You could not do it.
On tempered instruments, it's just an approximation. Yes.
Yeah, but even if you go before Bach on non-tempered instruments, there was a constraint that they wanted to have it on one linear keyboard.
Yeah.
One after the other. When you do that, you will switch between different tonings.
Yes, you cannot.
You will switch between different tonings, but it will be a higher level of harmonics.
Yeah. It's certainly a very interesting idea. I think we should do this, Thomas.
Yeah, let's do it, of course.
I was also thinking in this direction, following what Christian said, that bringing up clarity in listening. Because if you're not playing with notes and you're more in the harmonics, then you're actually listening more closer. You have to listen to subtle changes.
I think it would also correspond to what Thomas was saying, that you enter rhythms, you enter patterns of rhythms, and then actually the tones in themselves would also be patterns of rhythms, you see, of vibrations. Huh? But it would be not exactly pre-Bach, because pre-Bach there was another constraint, namely they wanted to be able to play it on a keyboard. So what you will do then will not be able to be played on a keyboard.
Yeah, and another reason why I'm thinking that it makes more sense that you go into such fractions of sounds is because if you're looking at the simple chemical reactions, when you have only 3 species, they're in a more complex structure, they would maybe not even be discernible for us. So in a sense, they would be very similar. So to me, it's such a big jump to create an orchestra for such a simple rudimentary reaction. Rather, they should be so close to each other that you can barely figure out which one is S1 and which one is S2. They shouldn't be so different.
This is where art science begins. So we can now kind of collect all these ideas and explore them in using the system, and then we can kind of evolve. And this is why we were so humble and so realistically humble at the beginning. This is just like the baby step, just to show the proof of concept. So this is kind of a new, or not new, but our new way to make sounds.
I'm ready to eventually reflect on how to make it into fraction, because I've reflected a lot about that earlier on. What kind of fractions? Because there's different ways to choose the fraction.
Yeah, I think that would be very interesting for a seminar, Diederik. Maybe you could we could schedule your talk about this in the future. Of course, we have, so just coming to the idea of what's next. unless there are more questions now. Anybody?
Well, I wanted to make a remark about what you said about it makes it interesting when you have input from the outside. And I think it's a general question of self-organization. On the one hand, self-organization leads to an attractor. An attractor, by definition, means that you reduce the freedom, but you can have very simple attractors, like a point attractor, and then nothing happens anymore. You just hear one tone, or you can have a very simple limit cycle, like you hear 3 tones repeated all the time. Or you can have chaotic and strange attractors, where there are all kind of interesting but not exactly the same recurrent patterns. But in reality, what happens is that you have an autopoietic system like an organism, which has this kind of regularity inside. It means some degree of repetition. But then, of course, you have the input from the outside, which is to some degree unpredictable. And it's that interplay between unpredictable disturbances from the outside and to some degree predictable regular dynamics of an autopoietic system that creates indeed the interesting things. And I made an analysis of stories, so narratives, in this way. Like a narrative is when an agent, where the agent has some predictable desires interacting with an environment, where the environment challenges the agent in a non-predictable way. But knowing what the agent wants, you can to some degree predict the reactions of the agents. And it's this sequence of the agents experiencing unpredictable challenges and then reacting to it partially predictably, partially unpredictably, that creates an interesting story. So an interesting story is not the same as an interesting musical piece, but there will be some degree of the same kind of dynamics. That in a musical piece, as always, you have a combination of predictability and surprise. Maybe in a musical piece, compared to a story, there will be more repetition. That means more predictability and relatively fewer surprises. But having the surprises from the outside is indeed a way to make your musical piece interesting. So suppose that you generate a pretty interesting attractor, an organization that repeats itself but in a non-obvious way, and then from time to time you inject some species from the outside, and then each time the organization has to adapt to this new injection. And one moment it may react in one way, and another moment it may react in another way. But after a while, you will expect the organization to find back kind of its rhythm. And that, I think, is what makes a musical piece interesting. That you have this, to some degree, recognizable pattern repeating, but which is then regularly challenged and varied, and that's what creates then variations, speeding up, slowing down, increasing, adding sub-themes, etc. So I think as a general principle of self-organization, it's important this kind of combination of an attractor, that means repetitive patterns, with injection of challenges from the outside that force the attractor to adapt.
I think this is very much in line with what Thomas already said of the inflow and outflow. I mean, adding, it could be a nice way to model
that clear.
this.
I wasn't as clear as Francis though, but that's the core. And it was an interesting discovery for us when trying the reaction networks to see how inflow and outflow, you can control the situation to reach more periodic dynamics or more chaotic dynamics. It's just parametric gain. So, which would be the different responses of the self-organizing system, kind of more random choices or more regular choices. So, yeah. So it's, I guess it's 2 hours already from the seminar. So we should, we should be closing, and I would like to announce or ask if shall I announce, Karsten? Are you in health in good health to give a seminar on 2 more weeks?
I think so. Yes, I am. Yeah, and took a lot of notes, and I guess I will need to study all the past videos the second time.
We can facilitate the code, and whatever you need, we will be here for support.
Okay.
So the next seminar will be then Karsten, and there is a to confirm seminar by Olaf, and then to confirm seminar by Stan. So we will continue, let's say, discussing and kind of reflecting on different aspects of this. So we would like to go over with more talks covering different aspects, while we keep with these lines, and the line will still evolve. At some point we might apply for a grant or something to make something like really serious about it, and then we might shift to work sessions instead of seminars, like so but we need to find yet the topic. So also Orion is proposing a seminar, but I haven't yet replied to that. I don't know really, I didn't read the email yet. But so you are all welcome to suggest your seminar if you want to talk. This is an open space for reflection and ideas. So Katarina, would you like to say something?
No, I have posted in the chat.
This about the subscription.
Right. If because, most of us here are on our mailing list, but for people who joined in finding the event somehow differently, you can stay in touch by joining our mailing list. Oh, I see that I posted the same link twice.
I might just want to make a little bit publicity. We are planning to make a parallel seminar series with Shima about health and well-being, also from Clea, also this interdisciplinary meeting of people with different experiences, and also speaking about more practical experiences, not just the theory, both the science and the practice of what to do for well-being, longevity, and health, etc. So that will probably be on Tuesdays every 2 weeks instead of on Fridays every 2 weeks. But you'll hear about it if you are subscribing to our mailing list.
Good. Clea is on motion. Nice.
I just wanted to add that I had some conceptual concerns with this trajectory that you're following right now. So I wanted to challenge you and be the bad guy. But there's no time, so I'll just wait for us for another occasion. Anyways, thank you, everyone.
Okay. Well, I'm curious. I'm curious for your comment. Well, yeah. Then thank you, everyone.
To come back for the next one.
Perfect cliffhanger.
Yeah.
Okay. Stay in touch.
You do a seminar also, Katarina?
Yes, I was offered and I declined. But I declined at this point. So at the later point, yes, I would love to.
Okay. Nice.
Okay. Goodbye, everyone.
Wish you a nice weekend.
Goodbye.
Bye-bye.
Thank you.
Thanks a lot. Bye-bye.
Bye-bye.
Little announcement. Don't leave.
Bye. Okay.
We will. It's time for announcements. Now I see Catherine. We will have another workshop on quantum theory and cognition, sort of quantum cognition, but it's a little bit more general, more epistemological approach for those that are interested in paradoxes of cognitive science or irrational behavior, and also interested on the weirdness or obliterating thingness. I don't know how to say the title of that paper from Catherine, but she will be giving a talk, and 2 other researchers from the United States on quantum computing to model human memory, and a psychologist from the Netherlands, can't remember, Groningen, might be, yeah.
Yes.
From there, he will be speaking about the measurement problem applied to psychology. So yeah, interesting, and it will be posted to somewhere. You will receive that, just to let you know that it is coming. Okay. So, see you.
Goodbye.
Yeah.
Bye bye.
Goodbye.
Thanks,
Bye bye.
Goodbye.
Bye.